Vectors in dot product. This is covering section 6.4. We're going to cover topics like the dot product of two vectors, how to find an angle between any two vectors, and how to find work dealing with dot products and forces and vectors. The first part is called the dot product. This is actually quite an easy concept. Formulas for you is written right here. When I dot two vectors together, now this looks like a multiplication symbol, but it is pronounced just dot. It is similar to multiplication, but it is definitely not a multiplication process. Dotting two vectors together is simply multiplying their x coordinates, multiplying their y coordinates, and then adding the components together. So for example, if we had vectors 4, 5, or vector 4, 5 and 2, 3, if we dotted these two vectors together, it would look just like this. 4 times 2 plus 5 times 3 equals 23. If we dot the other vector, 2, negative 1, 1, 2, we get 2 times 1 plus negative 1 times 2, which is equal to 0. The result that makes a significant contribution to your problem is when the product is 0. You can see by the pictures on the right side of the screen, you have the vectors 1, 2 and 2, negative 1. Clearly you can see the right angle between these two vectors. If you look at the other vector, or the other problem, you have 2, 3 and 4, 5. These vectors are absolutely, clearly not perpendicular. They're actually more closer to parallel than they are to perpendicular. But they have a specific angle, a very small angle between the two of them. So the dot product, what you want to remember about the dot product is simply that if I do a dot product and the dot product is 0, that automatically tells me the angle between the two vectors is perpendicular, or we say 90 degrees. Okay, well, what happens if I have two vectors like this and I would like to find the angle between those two vectors? Well, this is how you'd find that. Finding angle between two vectors is done with this formula. Now, the cosine of the theta, the angle, is equal to the dot product of u and v over the magnitude of u and v multiplied. So here we have a vector 4, 3 and 3, 5. We're going to find the angle between the two of them. Now I'm going to need their dot product. That's easy enough. And I'm going to need the magnitudes. If you remember, magnitude of any vector is basically the Pythagorean theorem if we have the components of my vector. And so it would be simply the first part squared plus the second part squared, and then we're going to square root that value. So if I do that for my two vectors, I get 5 and the square root of 34. You can see as we plug those in right here, we find the dot product on top, we use the magnitude on the bottom. Once we find the inverse cosine of these values, we find the angle between those two vectors, rounded to the nearest tenth, is 22.2 degrees. Okay. Work. This is quite easy, actually. You need a formula. The formula is, well, by definition, work is the amount of, it's a force done over a certain distance. And so we would like to know the work done. We take a force, we multiply that by the distance over which the force was actually applied. The formula can be done by a dot product or by a projection. And I didn't write, if you're looking along in your book, I've kind of modified that value just a little bit. The projection can be kind of simplified into kind of this little scenario. I went ahead and did that for you, make it a little easier. Basically, it works like this. If we have a force that's about 45 pounds being applied to a table that the angle of the force is being applied to 30 degrees above the horizontal. Okay, and this is the amount of force required to push the table across the floor. We want to know if we drag the table 20 feet, how much work was done. Okay, now we are measuring forces in pounds and we are measuring distance in feet, so our unit at the end is going to be foot-pounds. It's kind of weird, but just kind of, it's always distance dash force. And so it looks like this. We're going to use the second of our two formulas because they kind of gave me the angle and the magnitude of the force and how far I was going to actually push it. So it's kind of preset just to plug it in. So it's the cosine of 30 degrees times 45 degrees, or 45 pounds, that's my force, times the 20 feet that I'm actually going to be dragging that object, which would simply give me 779.42 foot-pounds. And that is basically section 6.4. Now, naturally, there are much more difficult problems, particularly word problems. Be careful, and we've already did this one in a different tutorial, but if you have the force being applied up an incline and you wanted to know the force required to keep that object stationary or to push it up the incline at a particular angle, okay, you will see some of those problems in there. Remember how we do those and create our little similar triangles. Other than that, I think this section is fairly straightforward. Check the formulas out. Really, what's important for this is a real formula-driven chapter or section. Make sure you write those down or print this worksheet out and bring it with you to class.